All right, great. So, all right, so let's start with. So, today we are going to go with session number 4, right? Great, great. So, let me turn on the video. You can see my screen. All right. So, if there is a delay, please let me know because I'm suspecting a delay in the video today. All right. Great. So, yesterday we left with the voting problem. So, the approach clear to all of you with respect to the voting problem? Great, great. Awesome. And so if the approach is clear to you in the voting problem, so you have basically understood how would the join happen over big data using a distributed computing. All right. Just give me one more second. I'll close the windows. Correct, correct. That's exactly. Actually, the data frame merging in R has been heavily inspired by parallel computing and the distributed computing. Okay, okay. So, so Santana is saying if we can go over once, like a quick summarization. Okay. So, in all these four problems, what we try to do is we try to exploit the behavior of Hadoop where it sorts your data. So effectively, we try to convert all our problems into sorting. Okay. So we created our criteria of sorting such that our output, we achieve our output. Okay. So here, for example, we want to find out the worth of each voter. That's our first objective. So worth of each voter we want to find out. Okay, along with the votee. Okay, so what we want to do is for each voter we want to find out who he voted and what is the worth of the person who voted, right? This can be done if we sort on the voter name after merging the two. After merging these two lists, if we sort on the voter name, then votee as well as worth will come together with the voter, right? This way, so here, the how can we bring it together? By just using uh, by using Hadoop to sort our data based on this key. And that's what we did. So here you can see that the data for A, meaning data as in the what is the worth of this voter and who all this person voted, brought together by Hadoop. Okay, all we did was we form our criteria of sorting as the voter, name of the voter, and here we have. Now, as a next phase, what we did was we gave out the worth of all these people by virtue of voting. So, by virtue of A voting for to B got 5. By virtue of A voting to C got 5, and so on for all these things. And afterwards, again, here what we have done cleverly, we have created a key. We have created a key such that if you group it, if you sort the data by key, all these values will come together and we can easily sum up. Okay, so when this data gets sorted and grouped, all the values, all the votes, all the worth of votes will come together for each of the person who was voted. Votee will all the so we can just simply sum up these values and we'll get the worth of the votee. Okay, so here the next clever thing is we did was we formed this new data where the key was the person who was voted, and the value was the worth of everyone who voted for that person. Okay, this way we are able to bring our results. So although it took us two phases of map reduce, but we will be able to handle humongous data. We'll be able to handle humongous data this way. Okay, now what is the catch here? Catch is if this list is smaller. Okay, if each person is voting to a million people, then this list is going to be fairly big, and then we can't handle it. Then we will have to come up with another strategy, another way of forming key value pairs. Okay, those things have been done really well by other tools. We will explore things like pig and hive, where when they join two tables, they do it a little better the job than we did, right? So you keep that in mind. Here there's a challenge. In case one person voted to more than a million people, then it becomes a problem. Here the assumption is one person is voting to maybe 100 people, maybe 200 people. That's all. Okay, because this array will become really big and the value reduce will get will be humongous, and then it will not be able to solve if a person is voting for million people. So this is a although this is a safe assumption, but in case of Google kind of ranking. Okay, so if those guys who are wondering why are we talking about this problem is interesting. Is interestingly the problem which was solved by Google by the way of PageRank. Okay, so it's partially like a PageRank algorithm. This problem. So the way it works is in case of Google PageRank. Okay, in Google PageRank. So okay, before I telling you, did I tell you about the Google PageRank yet? No. Anybody interested? All right. So let me just quickly describe why what is so important about this problem. All right. Now let's say there is a website called let's say Hot and Works website. Okay. Hot and Work website has a web page. Okay. And it's referring to what? Some other website, say apache.org. All right. Like this. Now there is another website, xyz.com, okay, which is referring to hotandworks.com. Okay, so xyz.com is referring to Hot and Works on their web page. xyz.com is saying that please see Hot and Works for more information, or No Big Data is referring to Hot and Works or Cloudera. Now, Hortonworks website is people like Hortonworks are all referring to Apache.org. Okay, so if you see it, it's more like these websites are saying that that place is a better place, place is a better place for more information. Okay, so the more people are voting for somebody, the more pages are linking to some page, its value becomes very high. Okay, so if you see this diagram, so let's say there is a page and there is a B page. Okay, they are all referring to, say, somebody like C. Okay, C, and then there is another website D who is also referring to C. Now, if you see here, and there is E who is referring to B. Now, so on their there is website A, website B, website C, website D, and website E. So the rank of, imagine that by default we give the value to the refer as 1. E is also 1. Now, since E is voting to B and B has got its by default value as 1, so the B's value becomes 2. Okay, so E also voted for B and B has got default value as 1. Now B's value is how much? 2. Similarly, D's value is 1. Okay, so these are the websites in itself. They all have 1 vote. But by virtue of voting to each other, their values are increasing. Their values are increasing. So B got 2. Now, can somebody tell me what will be the value of C quickly? It'll be 5. Why? 2 plus 1 plus 1, 4, plus 1 was the default value. All right. So now what do you see here? Now let's say there is another website now being referred to by somebody like C. Okay, let's call it F. Okay, and there is another website called CFG. Okay, that has got a value, similarly that has got a value of 10. Now what you can see is the more the people are referring, the more is the value becoming higher and higher. This is called page rank. If something has got a higher page rank, it will appear higher in the Google. So this was the default earlier algorithm. Okay, now this combined with lot of other factors is what is Google as of today. But this is the main reason why Google came into existence. So is that clear? All right. Now if you see, yes, the value of f will be 16. That is correct. So now you can see that these websites are voting to each other. Okay, and they have got their initial strength, they have got their initial values. So what you do is you run my algorithm, whatever we did, and whatever values you generate at the end of first cycle, you keep on doing it every day, and one fine day you will have this final value. Okay, the algorithm is far more complex than what I have done. I have tried to simplify it. Okay, I have tried to simplify it a lot because here we have not considered lot of things. First, we have not considered the cycles. Cycles as in C, A is voting to C, C starts voting to F, F starts voting to back to A. then what we'll do in those scenarios. So those things are taken care by Google in a different manner. Okay, so this is the PageRank algorithm as we know, and that's what, if you see, one page will be at most referring to 100 pages. If one page is referring to more than 100 pages, then there is something wrong with this page. Okay, so that also you can handle it here. So still our algorithm would work to some extent. Sounds good to you? All right. So that is the significance of this voting problem, because the whole map reduce was invented in order to solve ranking problem. Okay. If you read the basic paper on Google Map Reduce, that was basically invented in order to do the ranking computation. All right. So these kind of small, though these problems look fairly simple, and but when you see the practical implication, it's tremendous. Now, the next thing we talked about, there are few cases when you should not be talking about MapReduce. There are few cases where you should avoid using MapReduce. So, like with every other tool, MapReduce also has got limitation, and you should not try to apply MapReduce everywhere. First, if the job can be done really well on a single machine, do it without MapReduce. You'll be everybody will be happy. Okay, and the reason is, when I say job can be done, meaning if you see that today the job is being done on single machine, but after say 6 months down, we'll have so much of data that this job will not work, then you should do it on the MapReduce. All right. Then another one where next step depends on the previously computed values. There you should not be using Fibonacci series. You should not be using MapReduce, like for example, in case of Fibonacci series. And does anybody remember by any chance what is Fibonacci series? Yeah, just a second. Let me see if. All right. Good, good. So the wave, yeah. So the way Anand says that sum of previous two numbers, right? That is what is the third number. The next number, every number is the summation of previous two, which means for computing every number, you need previous two numbers, right? So there is no way to solve this problem using more than one computer. Even if you did, you will not get added advantage. Or can anybody suggest me? I'll be more than happy to see the approach. The idea is to generate Fibonacci series to say 1 billionth term. We want to generate 1 billion terms of Fibonacci series. Can we automate this? Can we parallelize this? Can we distribute on multiple computers and get it done? If we had to do simpler operation, such as if we had to do if we had to do something like cubes cubes of all the numbers from 1 to 1 billion, then this can be distributed, because for computation of cube you don't require the previous values, right? All right. So whenever your heavily depends, computation heavily depends on the previous computed values, then it is going to be very difficult to convert your problem into MapReduce. Even if we did say we used a central database where they started communicating, one map is writing the value to that database, other is reading from it. Although we will be able to do it, but it will be it will be very slow. It will be very slow. The added advantage of distributed computing will be negative. There is no positive advantage of using MapReduce. Third, in case your problem requires real time response as in a response within less than a second or maybe 2 seconds. In those cases, please avoid MapReduce. Okay, you must have seen when we ran word count, it took some time. The fourth one is when your algorithm depends on some global state. When same thing as Fibonacci series or computation depends on previously computed values, similar to that one. Let's say there is a central state being automatically changed, and every time your algorithm has to do something, take the next step, it has to talk to this central service that was going on. In those all cases, it's very difficult to get a good performance using MapReduce, because for each mapper it is going to hit that service. All right. Any questions still here? All right. Let me see what questions are there. Last point on algorithms, same as, so say for example, there is a central agency which keeps on generating these IDs, and your algorithm need to read this ID, and every time it does anything, it talks to the central database or some service that, hey, give me something, or what is the value of this thing. If your algorithm keep on asking the central service all the time, then what will happen is all the mappers will be asking this central service all the time. The mappers will get slow because of this, and central service will get bogged down by so many requests. Okay, but having said that, there are it is okay for algorithm to sometime access global state, because it's not, there are a lot of algorithms which basically need a global state, but you have to figure out the trade-off. Is accessing this central service is still faster than the single computer, or is slower than that? You will have to figure that out. All right. Now next one. Yes, you are right, Rajesh. Basically problems which do not need distributed system, plus problems which do not need real-time response. Here, that's the third point. In those cases, there is no point in going for MapReduce. Sounds good? Does this mean most of the cases it is for analytics purpose? That is very correct, Anand. So most of the time it is for analytics purpose. Building a search engine or building something on top of Hadoop using MapReduce is not great idea, but you can definitely use HDFS, HBase, and other tools on top of Hadoop on top of Hadoop, as part of Hadoop, you can use HDFS for your search engine. And along with that, you could use, if you want a real-time response, like in case of search engine, you could use things like Spark. Okay, Spark will be talking about in the last session. Okay, and there you will also understand that how can you do a lot of machine learning things onto the Spark. All right, now looks good to you. Now testing of a streaming job is probably the easiest one out of it. Okay, testing of the job is very simple. Whatever mapper you have written, you can use a command like this. Okay, a command like, let me copy it to separate file. Say you wrote a mapper program like this, and we can put dot slash just for making you understand. Say you wrote a shell file, you wrote a shell script. Okay, so you can execute a command like this and you will get the same results. Here you might use plus nr, whatever parameters did you use in case of your streaming job, you can use the same parameters here and you will get the same result. Okay, so in case you want to quickly validate what is wrong with your program, you can create something of that sort. Okay, whatever input file you are trying to churn, do a cat input file or maybe a small sample of the total input file and give it to mapper. Whatever comes out, you sort it, and then you run the reducer. So you run the same reducer code which you are going to give to streaming job. You will run the same program which you will give to the streaming job, and you will see that the results, you can quickly check whether it's giving correct or not. And this is probably, I like streaming job more than any other way. I mean, more than MapReduce Java, because it gives a very quick testing. So what I generally do is cat this, I create a sample file, okay, sample input file, and I say cat sample mapper output. Okay, so I generate these things, and also I keep my output ready and I just compare that output with this one. I basically diff against my standard output, whatever comes here. All right, this way I'm able to quickly test mapper and reducer easily. Okay, so this is a very quickest way to test a reducer or mapper. Alright. As a part of general strategies, you should always be testing mapper and reducer independently as well as together. Okay. So first is test on very small data and do not take first 10 record, last 10 records or something of that sort. Instead, always have a random sample of your input data, statistically random sample. Okay, because what happens is we get very impressed with the results by first 10 records or last 10 records, and generally these beginning records and last records are not representative of our total records. Okay, so you should use on a random sample of data. Okay, secondly, always test mapper and reducer independently. You prepare that, okay, this is what I expect from my mapper, this is my sample input file. If my mapper runs, this is what it should give. This is my reducer. It takes this kind of input and produce this. Now test it and verify that. And once both are verified, then you run the test case where both are tested in conjunction. You can think of it like unit testing and then integration testing. If you are using Java, then you can use MR unit, which we will talk in the next class. I mean, today itself. To test predictions, now the other is if you have built a prediction system, if you have built a system which predicts something, you should test it against a against the data set which you produce, which you already have. A real how should I say you have built a recommendation system. So you break down your input data into two sets. You generate the recommendation on first half and compare the result of your predictions against the real data. That way that way you will know how well do you compare against the reality. Sounds good to you? Now, any questions here? So this we will talk soon. There is no point in talking soon. Now, but one I will like to pile on upon previous questions. The so you need to do few things. You need to take those same questions, same four questions, and write it in your favorite programming language. If you are not very hands-on on any programming language, is then as problem the basically write in a pseudo language. Okay, write in any hypothetical language, that will be okay. Now next problem I want to discuss with you is this one. All right, so let's do it now itself. There's a huge text archive. Okay, imagine that you have a huge, say, whole Wikipedia at your disposal, and what you want to do is, or you have the whole chat history of all the people in the world. Now, what you want to figure out is when people are typing things, people are saying, "Hi, how are you?" So, you are basically giving the recommendation. As you must be using mobile phone, and when you type a word, it gives you the next set of recommendations. Okay? And this recommendation is based on what people generally talk about. Okay? And it's not a big rocket science. It's not a very difficult thing to do. All you need to do is do a fair amount of statistics analysis of words and you will get the results. A very simple analysis, a simple frequency thing, counting what all words come most frequently after a particular word. Say somebody typed hi, what are the top 5 words which come after this word in this given corpus of text? Okay, in this text, how many times, what are the top 5 words, the most frequent 5 words that has come after hi? We have prepared that kind of list for all the words in the dictionary. For all the words we have figured out that. Okay, so my question to you is, if you have to build that kind of recommendation, how will you use MapReduce? Or do you need to use MapReduce at all or not? My okay, yeah. So my question is, given a huge text, you have to prepare top 5 recommendations for each word that has come in this text. Okay, top 5 recommendation of the word successor successor word, as in when somebody types dear, what should be those five most frequent words which should give those as a recommendation. Yes, sort of that. Yeah. So how would you prepare that? Using MapReduce. Because this is a huge text. If you are downloading the whole world data, that is 500 terabytes. Okay. Uh, okay. Johnny's question is brilliant. Since we need instant results, how can we use MapReduce? So when you when the in the real life, what would happen is you will prepare these recommendations, save it somewhere, and save it somewhere on the server. When the user uh, types something, then this service will give out the recommendation from pre-prepared list of things. All right. So your job every night it will run, prepare these recommendations and save it in this system, and then save it in the service, and this service will continuously keep on answering people's question. You got the answers, Johnny? All right. So so where we store? We generally store in a service. You mean the results in the database? You could use Redis generally, because this is going to take a really fast approach, and a database like Redis or maybe a database like HBase would do a pretty good job. It will be partly incremental learning, but generally what people do is, because incremental is too much of a hassle, right? So people generally prepare the whole list again. Right. So Mark's question is, why wouldn't you pull random sampling? Right. Now, if we do a random sampling, it will not be a great idea. I didn't get this one. So we prepare all list of the whole words, whole world, a list of all the words that follow happy. Say there are 1 million words. Now, if I just pick five out of this, will that be a good idea? What we want to do is we want to figure out, when person types a word, what are the most probable words this person is going to type after the word he had just typed. I typed dear. What are the five most probable words which would follow this dear? The word dear. What are the most five uh, things? Okay. So Mark's question is, you will pull five words 1,000 times and then compare. That would be actually fairly slow system. If you compare, and still it will not be statistically really high, great. Okay. So if you think about computational efficiency will be better if we just compute all the words of this frequency analysis once, because what you are talking about is, imagine this: you have got, say, 50,000 words. For 50,000 words you have to poll 1,000 times for each, right? It will be 50 million times sampling of the data. All right. Yeah, but it's a good trick. And I'll also think about if we could utilize that kind of statistic technique. And people do utilize things like in Bloom filter. Okay. Now, Johnny's point is, can we find what people type mostly first and create a dictionary out of it and check there first? Good, good. But just, I mean, idea is exactly same. But the idea is, but what preparing dictionary takes too much of memory. Okay. New age day. Okay. Sarju, I did not get the your point. Okay, so basically, given in a huge text, let's just pull out the text what we have in big.txt, and what we want to do is for each word we want to find out what are the words that follow it. Okay, I think yeah. So can anybody suggest me an approach? Anand, Rajesh, Eric. So you have got huge text. Okay, what you want to do is based on that you want to figure out, say from this, the from is following content, right? And after a we have got vary, we have got top. If you have just this text, then how would you prepare this kind of list out of the whole corpus? So Mark's question is, how does this scale back by timestamp? How does this scale back by timestamp? Mhm. Or is it in line feed term order? No, I did not get this. So maybe I'm not great with the statistics. Okay. Johnny says that split each sentence into combination of two or three words and create an index of it. Great, great, brilliant. Okay. But I did not get why three words. Why not only two words? Because we are interested in only tuples. Okay. Anand says split whole files into two consecutive words. Okay. I'm assuming that you mean to say two consecutive words and store it in a file. Yes. Yes. Okay. Or file. Okay. Then I want to suggest only two ones because suggesting the third word based on previous two is going to be little different exercise, but on the same lines. Great, great. You guys are doing pretty good. I missed Mark's point. Uh, he was saying, let me just copy your answers. So, how does it scale back? Split each sentence into combination grade and create an index out of it. Split the whole file into two words. So, probably good, good. Eric is right. Perfect, perfect. So, all right. Now, all right. So, you guys are doing good. Split whole file into words. Good. And store it in a file. in a DB, not required. We can do it in a file itself. You okay? You could use two words also depending on yes. Go with starts with query. Starts with will be fairly slow. Instead, because here it's a pattern matching and it's fairly slow. And group by and get limits 5. All right. Instead, let's just try to use MapReduce. You are on the same line because here, when you create in DB, you are anyway going to use group by and then try to find out top 5, right? Same thing can be done using MapReduce. I'm talking to Anand. All right. And we have answer from Mark is split into two files, then key value pairs and ordering. Yes. Eric says I would use each word as ID and store a doc with top 5 words. That's good. That's good. All right. All right. So you guys are there, almost there. Okay. So let me go to the solution. Okay. So this is session 4's doc. Here you are. Imagine that you have this text. Okay. You have this text saying, how are you, Ram? Happy birthday to you and happy new year. Right? Your mapper will take this text. This text is humongous. This text is say 70 terabyte, or maybe say only 100 GB for time being. Let's just assume 100 GB. Now out of this text your mapper will generate this first word, second word, third word, fourth word, and so on. Okay. How are you? How are you? You and that's and then Ram, happy birthday, and to you, you happy and happy new. Now, yes, how becomes the key and R becomes the value. So do you see any problems with this approach? Yes, that is good. Finding top 5 will still be an issue. That is correct. Why would that be an issue? If imagine a word like R, if there are 1 million lines, there are going to be 1 million words that follow R. And in the reducer who will get a 1 million values for a key called R is going to be drowned in the data. So instead there are multiple techniques we could do. Okay. Anybody else, anybody, do you see any other problem? Do you see any other problem? Yes, we need to order by rank. We need to give rank to each. Do you see any other problem with this approach? Keys and values are same. Yes, that is right. Yes, end of the sentence. All right. Any other? So here you see you and Ram, ideally they should also be the tuple here, right? They should be also a pair here. But since it's in new line and our mapper is not, mapper gives us, a mapper gets only one line at a time. Each map function when it's executed on one line at a time. So there would be a minor issue. Any other problems do you see here? All right. So these are the three main problems. First, computation. Yeah, computation of frequency can be further map reduced because computation of frequency is going to be a tedious task here. Reason being, for one key, say R, there could be a million words, and all these million words will go to a same reducer. They will not be divided into chunks. They will all go to the same reducer. No matter, even if you have 1,000 reducers, they all them 1 million words will go to same reducer, right? So what you could do is you could do few more clever things on it. You could do, you could prepare, say, okay, you could prepare things like, out of this you could prepare how dash r and 1, how and r dash u. So these two pairs we put it as the key and 1 as the value. Okay, then you sum up the frequencies here, sum up the frequencies here, and then you can do this. Okay, all right. So this way if after summation we got some number like 60, we put a minimum threshold that though we will have only those pairs which occur at least 30 times. So this way a lot of pollution will be removed from the data, and then we can form the pairs easily. Now here we found how popular are these pairs. So after how, r will be coming 30 times. That's why this pair has got this much 1, right? So basically you form the pair, do the word count, and you will get the answer, right? But that's not our contention right now. The more important part we are having here is the last word in the line should pair with the first word of the next line, right? Instead of processing this text line by line, we should be processing this text sentence by sentence, right? Instead of processing this whole line by line, we should be processing it by sentence. Are you guys with me? These two words, there should be no situation when people type ram, we should be giving a suggestion called happy, right? Because they don't belong together, they are two different sentences. Are you with me? I'm talking about point number 2 and point number 3. Okay, so how do we do that? So all we are trying to say is, in the default map reduce, when we did word count, we got one line at a time in our map function. Can we make that better? Is that possible to make that better? Now Mark's question is, yes, now where does the weighted file go, and do you just reference the location from map where it is stored in HDFS for weighing the words key value pair in the map of the reduce? So weighted file will go into the HDFS. We just reference the location in the map, and that's all. Okay. All right. So this kind of situation where our map, yeah. So in case of map reduce, what we will be doing is we will be customizing the way we need to read the file. Okay. And we will be talking about this today itself. All right. And that is why we need Java. And this today's main title is how to do map reduce in Java. Okay, so we'll be dealing a little bit about in Java today. So in case you have you gone through my Java exercise? In case you have not, if you don't know Java, so who all are not familiar with Java? Okay, Rajesh will catch up. Okay, Mark will be able to take care of it. Okay, okay. So Johnny has done in past, so he'll be able to handle it. Well, okay, okay. I'll be cautious when I'm explaining things. I'll try to explain it such that it is language agnostic. All right. No worries, no worries. Okay. So the exercise, the objective is not to make you perfect in Java, but give, make you aware that this is how you can do things using your Java. All right. So everybody else is okay with Java? All right. Great, great. Now question is to you is very quickly, yes or no? The data generated by mapper is given to reducer and then it is sorted. Is that right or wrong? Exactly, Mark. Yeah. The way we use streaming jar, we will be using your jar. Okay. No, that is correct, Rajesh. So the answer to this question is no, n- no. Okay. So the output of the mapper is first sorted and shuffled and then goes to reducer. And then, all right. Now, next question, be a little proactive. I'll say true and false instead of no and yes this time. Okay. The mapper can only generate a single key value pair for an input value. Is that true or false? That is correct. Brilliant. So it will be false. Okay. So mapper can generate as many key as it wants, as many key value pair as it wants, because the traditional notation of map is it just changes the values of array in place. That is the traditional connotation of map. The traditionally the way we have thought about map is we have an array, we want to apply a function like square root, or something of the say we want to divide all the elements by 10, we want to add all the elements with 15. In those cases we'll say that we take this function whatever we want to apply on the whole array, and we say map this function on an array. So that was the traditional connotation of map. And that is why lots of people still think that in case of map reduce, it can only give out a single map, a single key value for the given input. All right. So that is correct. Now this one, yeah. The mapper always generates at least a key value pair Is that true or false? Let me make it correct or wrong. So a mapper, does a mapper have to always generate key value pair? Can't it just say I don't want to generate any key value pair? Are you sure? So in your if in your mapper I choose not to give out any output, it's okay, right? Mapper does not always have to generate the key value pair. It does not have to generate the key value pair. Okay, so when I say always, it means that for some, say we had an input text file, and that text file did not have a particular word. There was few blank lines, or few lines only containing punctuation marks. In those cases, for those lines, mapper doesn't need to generate an output. Make sense, Johnny? So so it will be, yeah, it can just skip saying I'm not giving any output to you. One is it gives key as something and value as null. That is not still it's giving out key value pair. But sometimes it can say that, oh, I don't want to print anything. Let it go. I'll pass. Yes. So based on the logic of generating key value pair, the mapper's output is determined. Yes. Yes, that is very correct, Rajesh. So Eric, you got your answer? So it's up to mapper whether it doesn't want to give any key value pair, or it wants to give some key value pairs, or it want to give multiple key value pairs. It's up to the mapper function. For some input, for because this mapper function is going to be run per record. Per record means per line in our word count example. So for some lines, for some records, it may say I'll pass. I'll not give any output. Sounds good? Okay. But if okay, let me understand. But if does output it will be a key value pair or collection of key value pair? Yeah, yeah. It can give a single or multiple or nothing. All right. It'll be giving a collection of key value pairs. All right. Next question. By default, there is only one reducer in case of streaming job. Is that yes or no? By default, there is only one reducer in case of streaming job. That's correct. Anybody else? Yeah. All right. Yes. So by default, Great. Now, what is the role of job tracker? Now, let me answer Johnny's question. If there are two mappers by default, if there are two mappers by default, shouldn't be there two reducer needed. So Johnny's question is, so that's a smart thing. What Johnny is suggesting. Let me put it here before it goes down. All right. So yeah. So yeah. So what? So this is one strategy, and there is always new strategies are coming up. That what should be our default number of reducers? For example, all the code generated by pig we'll talking about in after a few slides. That pig automatically generates the map reduce code for you. Okay. Now that guy, what it does is when it notices that your input file is bigger than 1 GB, so if your file is n GBs, it will create n reducers by itself. Okay. So so there are multiple techniques people are using. Okay. So there is always a requirement to do some sort of intelligent thing on top of your data. And streaming job choose to have the default behavior really dumb, which is one reducer. Okay. While the other tools, other smarter tools which are built on top of MapReduce, they try to intelligently guess how many reducers will be optimum. All right. Now that was a good question. Santana is saying B. What is the role of job tracker? Great, great. So all of you decide the all of you are correct in this. Let me go through Mark's question. After you determine the correct distribution, you can choose more than one reducer. So it's not only the distribution of data which matters in case of reduce. Imagine the frequency of characters. There was a problem we discussed in which we were counting frequencies of letters, right? There, all no matter how big is our data, reducer is going to get very small data. Okay, and reducer cannot be ignored no matter what. Okay, so reducer has to be there because it has to combine data from multiple mappers, and therefore in the frequency of letter count, no matter even if you have 100 terabyte of English text, still you require only probably one reducer, not more than one reducer. All right. So so it will depend on what problem are you solving, not alone the data. Heuristically, heuristically based on history of the problems, it is generally conceived that more the input data, more the number of mappers, and hence more the number of reducers. That's the general heuristic speak. Okay, so does Hadoop support Derby? In what sense do you mean? Okay, yeah, let's talk about this. Maybe you just drop me an email. I'll answer that. That will be better. Great. So the answer to this question is B. And then we have got this. The map logic is executed preferably on nodes that have the required data. Is that correct or wrong? Is that yes or no? So map logic is preferably executed on the data on the nodes that have the data. Yes, that is correct. Next is map logic is always executed on the nodes that have required data. What is going on here? Map logic is executed preferably on the nodes which have required data. Answer is yes. Okay. Now here there is a keyword is always. That is probably I should have highlighted. Okay. Here the keyword is always. So correct or wrong? Map logic is always executed on the nodes that have the required data. So it's a typical linguist question. First one was map logic is preferably executed, and now we are talking about always executed. What if the node on which the data exists, all the three nodes on which the block exists, all three nodes are heavily busy? Would it say that I cannot do your job? Yes, so Eric is right. It tries to execute the logic closest to data as much as possible. Okay, so the sentence is wrong. The sentence is the answer to this is no, or all right. Now I missed few points. That is the whole purpose of Hadoop. Yep. Whole purpose of Hadoop is to try to run the data, run your code closer to the data. So there are multiple schemes, multiple strategies. We will talk about data locality optimization, which essentially means Hadoop will try to run as much as possible very close to the data. First attempt would be to on the same machine. Second will be on the same rack. Third will be in the same data center. And when it can't do anything, it might have to access the data from other data center. Okay. All right. Now Santana says that since admin node knows where the data is located, the task tracker can call the required nodes. Yes. I missed your question, Anand. So, okay, okay. Great, great. All right. So you got the answer, right? All right. Now, where does Hadoop store the result of reducer in HDFS or local file system? Quickly, that is correct in HDFS. All right. Moving to the next question. So let me finish. Let you finish all the answers. So let me move to next question now. Where does Hadoop store the intermediate data, such as output of map tasks? In the HDFS, local file system, or memory? Are you sure? So it stores in local file system. Part of it goes into the memory that keeps on getting written into the local file system. The output of the map tasks goes into local file system. Sounds good? No? Because in case this data intermediate data is fairly useless, meaning as soon as this map reduce task is over, there is no need of this intermediate data. It can be deleted immediately. Okay. So it would be better if we don't put it on HDFS because that would be too much of an overhead. That would be too much of an overhead. All right. So can we set it to put it on NoSQL DB? I'm not sure. I'm not sure because this is done with a heavy local optimization. For example, the way Hadoop performs this task is there'll be a kind of a circular list. In this circular list, all the map tasks that are running on for a particular job, they will all be writing key value pairs into this circular list from one end, and from another end, all of this will be saved to the disk. Okay, so this is a heavily optimized situation, right? It would be too much of an overkill because we generally use a database when we need a central storage which need to be accessed by all the people. If it's not required, we would just generally use a normal local file system. All right, make sense to you? So it will be first done into the memory, then into local file system. But but finally it will stay in the local file system. Memory, it will removed from the memory. All right. Now one more question, final one. The whole of the HDFS block on a node is fed to the mapper. Yes or no? Anybody? Okay. Here the keyword is whole. The complete of the HDFS block. That is correct, Rajesh. Good. So, if you remember when we talked about HDFS block, the block is a result of ruthlessly cutting the file into 128 MB, right? We just cut it. The HDFS, while storing in HDFS, your file will be ruthlessly split into these portions. Whether the boundary is in the middle of word, boundary is in the middle of line, it doesn't care, right? If we are doing a word count on such a block, that means we might end up having very awkward results. Half of the word, one word being counted as two, half of the word as counted as a full word, right? So, or maybe if you are working on a bigger word, say you are working on, say, what do you call, multi-byte letters. For example, the Hindi words or Chinese words, Chinese characters are built using multiple bytes. So there are chances that half of the letter went to one block and half of the letter went to another word. Yeah, Unicode is the proper way to say it. Thank you, Anand. Yeah. So if you are talking in terms of Unicode, there are chances that half of the letter goes to one block, half of the letter goes to another. Make sense to you? So that's why the whole of the HDFS block cannot be fed to the mapper. Therefore, we create something, a representation, a proper, you can say that a logical view on top of a block. We call that input split. We will go into the details of how to create your custom input split. And this input split will be able to answer the question with which we started the session, the one where we were we were basically creating the blocks based on creating input split and records based on line by line. If you want to create sentence by sentence, how can we do that? Make sense to you? All right, so here we go. So, very good question. Thank you, Rajesh. If the blocks of data is in two different nodes and a split is created using, say, you come up with a scheme that I want records containing 10,000 lines in one shot. My mapper should get 10,000 lines in a single shot. That's what you come up with. Say you are doing a frequency analysis of characters and you realize that it will be more optimum to handle 10,000 lines on a single node, single mapper, right? In those cases, it might have to read two blocks to prepare the input set for your mapper, right? And therefore it has to read two different blocks. Now question is, where would such a scheme, where would your mapper execute, on the machine containing block 1 or on the machine containing block 2? Okay, so the general strategy is that you tell mapper reducer, that you tell Hadoop that, hey, here is my code and I want to run it. Okay, so based on this file, so it will basically still run on the way where your block 1 resides. Okay, it will be run where your block 1 resides or maybe block 2 resides. All right, so generally what happens is when you create input split, generally you will still have two mapper 1 will consume almost whole of the data from block 2. If there is something left, then it will be fed to the second mapper. Okay, the second mapper, although it will execute mapper on both nodes containing block 1 and block 2, the second mapper will give no result at all. That's how it generally works. So by default, assignment is on all the nodes, and it's up to the input split whether to give an output to the mapper or not. Sounds good? Is everybody with me, or did I move a little more ahead? All right. So moving on. Now the question is, now today we want to discuss a little bit about Java. So let's start with why do we need MapReduce in Java? First, the whole Hadoop has been written bottom up in Java. Reason being compatibility. The vision with respect to MapReduce is it will be running on lots of kinds of data centers, lots of different kind of nodes. So the only way to do it is using Java. Okay. Even though Python could have been an option, but again it could have become a little more difficult to manage the support on various machines. That is why Java was chosen to write Hadoop, and hence we will talk about MapReduce in Java. Second, Hadoop provides a lot of knobs, lot of ways to control the behavior of MapReduce in Java. Okay, so here are the steps. So first of all, you should download Eclipse. Okay, Eclipse make the life easier for everybody, including myself, who is trying to explain things. If I have to explain the same thing using normal basic Java, it will be a little more difficult for me. Okay, so you download a basic version of Hadoop, a basic version of Eclipse. Eclipse is a visual editor in which we'll be editing the code, so that this first one would be sufficient for you. Okay, Eclipse IDE for Java developers. Okay, download it for your own machine, find out whether your machine is 32-bit 64-bit, and download that accordingly. Okay, most likely your machine is going to be, if it is recently updated, then it would be 64-bit. If you are on Windows, you can say right click on my computer and go into the details. You can find that out. Otherwise, if you are on Unix, you can say uname minus a and you will see the details whether your machine is on uname minus a, and here you will see the detail. Mine is, it says 64 at the end, it means it's 64-bit. Okay. All right. Now here, now once you have installed Eclipse, create a Java project. Okay. Add all the libraries. Okay. A better way to do it would be a better way to do it would be you go to my courses and there you will see a project. You'll see a nice project here. Here you have the whole sample project. You download this sample project and all the libraries that are required for this project will be available in one of the folders. Is it so? I think what will I do is I will try to stop the recording and start again. Okay, maybe it is because of that. Maybe when it completes 1.5 hours of recording, then it becomes slower. All right. So, so Mark's question is, does it support Java 8? Okay, it does support Java 8, but you write your code in Java 8. But here, when you talk about compatibility, so let me just go to training here. Okay. All right. So here the mapper we have changed. So is it slow now? Still slow? The switching between the graphics? Rajesh? The lag is there? Yeah. I mean keynote. Slide number 30. Now I'm switching to 31. Now I have reached to slide number 31. So do you see 31 now? Awesome. So it was because of the recording. So if you have the recording continued, so this thing has introduced a bug. Good that we have figured it out. So just the only downside of this approach is you will see two recordings of today's session, part 1 and part 2, in the learning management system. All right. Now the strategy here is we'll create a Java project. Okay. Here there is something called mapper. And what is going on here? object text long writable. Let me just fix the code. There has been some bug introduced by typing somewhere. Just give me a second and we should be up with it. So we have stub mapper, which is object text long writable. Here we have this object text long writable. All right, now it should be okay. The problem is gone probably. Two more places. MapReduce driver object text long writable. This is correct, and this is text. Okay, we got it. Okay, there are still few errors left. All right. So now we are in peace. Okay, so good. So we installed Eclipse. We created a new project by going to new and say Java project and give a project name and give a class name. After that, you will have a new project. Under that, you create, I mean, there you just created a blank project without any classes or anything. Now you create first the mapper driver. So first you will create a mapper, stub mapper, and then you will create a reducer, and then you will create a driver. Okay. And what goes where again? Here, stub mapper. So when you're creating a class in Java, you always, every file generally has one class. So you say, this is my class, it extends something. Okay, it extends something called mapper, and it also says that in what form it is extending. It's saying that my this particular mapper is going to have input in the form of object, and then the input would be in the form of key value again to the mapper itself. First would be object and the text, and the output which will be given by the mapper would be in the form of key and value, right? and this key is going to be text and value is going to be long. Okay, so let's take a break for 10 minutes and we come back. All right, so let's take a break for 10 minutes and come back after 10 minutes. Hi, I'm back. Are you guys back? Should we start now? Is voice audible enough? And my screen is not flickering, right? It's going good. All right. So what we were talking about, should we start? Is everybody? Oh, sorry. I'm sorry. Now you should see. I'm on 31, slide number 31. Okay. And then you see why in Java, primary support, then this. All right. Okay. So let's start. So everybody is in. Okay, so we were talking about how to write MapReduce in Java. You have done basic things. You installed Eclipse, you create a Java project, add these libraries, all of these libraries, and these libraries are also provided as part of the project here. In the under the sample project, you download it, unzip it. Under it, you will see the libs folder. There, all the jars are there. Okay. So all the libraries we have made available. Also, these libraries come as part of Hadoop installation. So under the Hadoop folder, you will see Hadoop libs, and there you will see all of these. Okay. Also, it's a general matter of practice to change your JDK to a lower version, or even if you are not changing this, at least change this. Okay, change the Java compiler setting to 1.6. Why am I asking you to do that? Reason being, when you are working with when you are shipping your code to some remote systems or your users, you should always be building against a lower version of Java. Reason being, in case on the target machine if you have say you compiled for Java 8 and on the target machine it is Java 7, your code will not run. But vice versa is true, meaning in case your code is compiled for Java 5, it will run in Java 8. But if your code is compiled for Java 8, it will not run in Java 6. Alright, there's a general thumb rule. So always to keep a backward compatibility in your code, you intend to always compile against the older version of compiler. Alright, older version of JVM. So change these settings, and how do you change these settings? You generally go into properties, right click properties, and then under Java build path, here you have library. You can say edit and change it. Okay. And similarly, in the Java compiler settings, change the compiler here. Okay, the compliance label is here. Okay. So even if you don't change the library, at least change the compiler. You must change the compiler to a lower version so that your output is on the should run on most of the scenarios. Okay, your program might run locally, but if your server is having an older version of Java, and that's generally true because people do not upgrade their clusters so easily. All right, so it's a general practical tip. Now to create a mapper, you basically extend a class called mapper and override a function called map. All right, so let me clean it up for you to make it more clear. Let me show you this. So let's just focus on, I'm just cleaning it up for you. We'll talk about the other details later. So here we are saying that I'm writing a mapper. Okay, I'm creating a class called mapper under which I'll write my function called map, which will take, I'm just removing some more things, which will take these three arguments. So every time when we say mapper will be run, it is this function which will be run again and again. So somebody, Hadoop will be calling something like m- mapper equals new stub mapper, and then for each line line dot each line run mapper with the line number and mapper.map run it with line number and line as the text and pass a context thing to it out of the in, and it will assume after the map finish it will put into the context the key and the value. Okay, so again avoiding the confusion, so this is what Hadoop would be doing internally. It will create the instance of your mapper, and then for each line in the input it will run your mapper. Okay, so here we have said that we expect the input in this format text, the key should be in object format, and the value should be text format. Okay, and where did we first declare it? While extending from mapper. In this slide you can see, while extending from mapper, we told that our stub mapper is a kind of mapper. Our stub mapper is a kind of mapper which has these key value types. Okay, mapper will take object and text as the key and value, and mapper will give out text and long as the output. So whatever you have here, these data types is what you will have. You can only write those kind of data types. You see long writable and text. If you had here the int writable, then you will have to give out, because here you are declaring that my mapper gives out key value in this data type. Okay, so Java makes it very, very type safe. It enforces it that whatever you have declared, you give out exactly the same thing. So if you have declared here that my mapper gives out text and int writable, then you will have to write int writable here. You will have to say context write new text comma new int writable. Right, so that's what is all about declarations. Now going ahead with further details, so what did Hadoop give to your mapper? First, it gave you the line byte count from, because mapper will be running multiply on multiple machines. So this particular, it will give you the line number, as well as particular text line, and it'll give you on what byte count does it start. All right, that would be the input value given to your mapper. And what did your mapper do? Mapper basically is converted that to a string, got the string out of this text value, and it splitted it by space. This is space. Okay, space or tab any number of times, split the line by this will create an array of words in each line. This will create array of words in each line. Now you iterate over these words, you keep on iterating over these words, and then write to the context the word and a number called 1. Is everyone with me? Right? So those who are not very greatly familiar with Java, let me try to show, had it been JavaScript, how would it look like? You will write something like a function called mapper where you will be given say byte count and line number, and you will basically have a context passed to the passed to you by Hadoop, and under the context you can write whatever you want to write. Okay, so you will do for word in line dot split, and we say this. I'm trying to simplify it if you okay, and under this we'll say that write to this one word at a time. We'll say word and numeric one. That's what we are trying to do here exactly. Okay, this is your code. From this bracket to this bracket is what you're going to write. All right, now that's how you write a mapper, and the way you write a reducer is in the same way. This time you extend the reducer. Text and long writable is what you get as the input to the reducer, because this is what your mapper will be giving out, and here your reducer will be giving out the data in some format and you will define it. Okay, you will define it here. Since I'm going to give word count, I'll say text and number of words. All right, so you run reduce here, and in reduce you are given two things. One is key and other is values. Values will be an array of ones, right? This is iterable, means it is an array of one, meaning it will have 1 comma 1 comma 1 comma 1 like that. All right, so all it does is it iterates over these values, sums them up, and writes it to the output. That's all. You can see that. So if I had to write in a very very simple way, this is how your reduce function would look like. Your reduce function will look like key and values. These values are an array. So all you do is for value in values, you sum plus equals value, and sum equals 0 in the beginning. So sum was 0, we iterated over values and added to the sum, and at the end of it we just or you can think of it like we have context here, and in the context all we did was we wrote key and the sum. All right, so that gives us the word count of our this thing. All right, now before we launch it, so idea could have been we just run the Hadoop jar and we tell it that hey, these are my reducers, these are my mappers, but that could have been too much of parameters and command line argument. So instead of that, we create a driver class. Okay, we create a driver class. Driver class says that job equals job config. So we create something called a job configuration on top of something, and after that we keep on setting the mapper and reducer for it like this, and we also specify these data types and other parameters like what is our input file. So this is how you set the input path. I'll show you in the actual code. You can see this. Okay, let's just trim it down here. So So in the job config, lot of things you can define here. Okay, so the purpose of this driver class is the entry point in your program. First, driver class is the one which is going to tell Hadoop that, hey, this is my mapper, this is my reducer, and these are the number of reducers I want in the runtime. These are the number of instances of reducer should be created, and my data input format is in this way, and these are the files which I want to process. Okay, so you can see here that we are saying my mapper, the name of the mapper class is this stub mapper which we just created. Then we are setting set reducer class, and we are telling that this is my reducer class, and also we set the key value pair. This is optional, although. Then there is something called partitioner. We'll not talk about partitioner right now. So we can actually customize a lot of things. Number of tasks, how many number of tasks do you want? Okay, number of reduced tasks. Similarly, we can also set the record length. We'll talk about this later. All right. Here, this is the way we added the input path. Here, arg0 means the argument passed to the stub driver. This is our entry point. You see, if the total number of argument to our driver are less than 2, it will give this kind of error. All right, so we will tell Hadoop to run our driver, and rest will be the duty of our driver to talk to Hadoop and say that, hey, please execute our map reduce. This way we say job dot wait for completion. This is the way we execute our job. All right, now, so once we have written our mapper, reducer, and driver, once we are done with it, what we are going to do is we are going to export this project as a jar file. Okay, so we can say that there is this word count, or we say that sg word count, and there we select sg test, and we go next and next. Okay, and save it. All right, now in my folder locally we'll have ls downloads, and we have what, sg word count. So it is just now created. Let's copy this onto Hadoop one. So what I say, SCP, if you are on Windows, you can use a utility called WinSCP to transfer data from your local machine to Hadoop one. Okay, Hadoop one, Hadoop two, wherever you want to do. Here we are copying this file to our server, Hadoop one nobigdata.com colon asgiri. Okay, and there we go. It's copying the data from sg word count to asgiri. I'm entering the password, so it has copied it there. Now let me just log in to the server. Go to asgiri. Now you will see that there is sg. Where is my file? Sg word count. Okay, the way to execute this is saying hadoop jar and sg word count, and we also have to tell the entry point. Entry point is sg dot stub driver. Sg is my workspace name, here package name, and now you can see we did not supply the other arguments, therefore it has given us this error, which means our program is working. Okay, our program is working. Now let's provide it the same folder. We call it as giri word count and we say input, and output folder we'll say as Giri, word count, and output we say sg dash java. So this is what we are going to do. So we are trying to execute, and also note that we did not have to copy this jar file into HDFS. That is something Hadoop will do it by itself. We had to copy sg word count to the local Hadoop file system. Alright, so it will be executing it on Hadoop 4 most likely, and right, because last time also it ran on Hadoop 4 because our file seems to have located on Hadoop 4. Okay, so it's doing here, it's doing the job. All right, now you can see that it's being run at Hadoop 4. Now it has created the output. You can check the output. You can say what was our folder name, this one. All right, now here we can say Hadoop fs minus ls. Right? You can see that there is a part created. Now, in case you had to change number of reduced tasks to 2, again you have to go through the same process. Okay, you'll have to go through the same process, and you will have to create the jar file again. Perfect, and there you go. So again, I'll keep this open as it was. Okay, that is overwritten. Now let's just run it again. I'll call it 1, and let's see what happens now. Okay, so it's being run parallelly here. URL to track the job is given to us. Also, you can go to the overview, and there you will see these are the jobs that are being run right now. Or are these the older jobs? Yeah, I think this is the one we are running right now. No, they're not. It's not that one. I think it'll be at the bottom. So I'm just trying to figure out where do we look for. Yeah. So it has run. Now this time the output folder would be this one. Let's check that. So you can say Hadoop fs minus ls. You can see this. Okay. Now instead of one file, now we have two part file like this. And overall time is how much? Here 36 seconds. And previously, how much was the time? Earlier it was So let me just try to do this. So elapsed time now was 1 minute, and earlier it was 49 seconds. So we increased the number of reduces and total time increased, right? Total time increased. And if we further increase number of reduces, there are chances that total time will again increase. Because unnecessarily we are transporting the data even though our reducer is fairly free. Alright? So if we have more reduced tasks, say 10 tasks running, it would not make any sense. They will still run on the same nodes. Alright? So that was our demo. Do you have any questions right now? So these are the steps we followed. We exported the jar, we copied to Hadoop 1 or Hadoop 2 or wherever you want to do. Then we said run this with the argument, and then we provided this in case. Yes, it is there already here. Here, this is where it is. Okay, this where it is. Now, now next question was to in case say your program is trying to do use some other jar. All right. In case your program needs to use other jar, say you are using some special functions on date time or anything, you could simply say minus uselib and provide a comma separated list of libraries. Okay. All right. Sounds good to all of you. So basically, by using minus lib jar, and you can write a comma b comma c comma d dot jar, and that's all. Okay. Say for example, you are trying to use Java Mail, and there is so many Apache libraries which you can use. You can simply say minus lib jars and then. So Santana's question is, suppose while running Hadoop command, I want to execute multiple jars. Okay. So what does it mean? So what you want to do is you have multiple map reduce phases, right? And you want to run those multiple reduce phases. So how would you do that? You cannot do it just like that, uh, because first map reduce phase will write the data into HDFS. So what you have to do is, if I'm in your position, there are two ways to do it. Okay, let's say let's say there is one this command, not this one, this one. Okay, so there is this command here. Let me write it like this. Okay, so there is one command like this, and I put a back code, and this. So this is my first jar, this is my second jar, and okay, most likely it is going to be taking the input from here and writing somewhere else the output, the resulting output somewhere. Okay, and I'm just utilizing Unix ampersand command, which essentially means in case the first one succeeds, please run the second one. All right. And basically this will create the data into the this will create the data into our HDFS, the first command, and we are going to use the same data in the second command. Sounds good to you? So this first command, we when we put ampersand, Unix runs the second command, this command, only after the first one is successful. All right, good. Or the other way would be to use Uzi. Okay, Uzi will make sure that the same thing. Okay, going ahead. Now, if you noticed that to to change a small thing, it took us a full cycle. If we make a further change into our code, it will have to upload it, compile it, export jar, and then ship it, and then run it on the server. And that one is a long process. Why? If it would have been great if we just test it locally. So you create a test case just like this one. Okay, you create a test case and run it locally. Okay, and the test case would look like there is a MapReduce driver. You add input instead of reading from file. You can add input like this. Here is the byte count. Here is the line. Here is the byte count. Here is the line, and so on, and feed it to your MapReducer by the way of you saying MapReduce driver dot run, and that will execute your MapReduce driver. So I'll show you this. So this is my test. Okay, this is my test, and I can say right click on it and say here run as JUnit test. And locally, if you see here, these are failing. Okay, these are failing. Why? Because I have not implemented anything here. This is also failing because I have not implemented anything here. But these are successful. What did this do? It did nothing, but it's dummy. The one which is important is this one. Okay, here ideally we should have done some sort of other aggressive testing. Here I've just tested whether the output size is 15 or not. Okay, and the word count is being printed over here. You can see the word count. All right, so if I add one more the here, and I can just simply say run it again. So that has become 2, but total number of keys are still 15. Alright, so we can, instead of going through the whole cycle of uploading and running on the cluster, we can keep testing it very fast here. The other benefit of writing test cases is that in case somebody is going to modify your Java code, still it will be your test case will quickly test whether this person has broken the previous test cases or not. Alright. So as a test driven development, you generally implement test cases first and then you write your MapReduce. All right. So go through this example and you will get a lot of, you try to run, try it, if you are from Java background, try to solve all those 4 problems using Java MapReduce. Yes, all of this is available here. You can simply go to course page, go to session number 4, under sample project, click open, and then you can download it. All right. So this was about writing a simple map reduce using Java. Now let's move ahead. So here we have this. What does it mean by input splits? So your block boundary is very rigid. Blocks are I mean, except for the last block of a file, every block is of 128 MB. 128 MB exactly that value, unless of course you have configured a different block size or you have set different block size for a particular file. So so in those cases the block boundary will still be rigid but of different size. So as you can see here that block boundary is here, although our record, it's in the middle of our record. Okay, so input split is generally created on top of the block boundary, which is logical, which makes a logical sense, such as the text input which is given to our map reducer was a complete line. It wasn't a half line, it did not have the half word. So those kind of input splits are created on top of blocks. Okay, that's what is called an input split. This input split has nothing to do with HDFS, it's a part of MapReduce. So every job can have a different input split, different kind of representation of blocks in its own way. All right. Now, another example is that say you have three lines, line 1, line 2, line 3. And block 1 is, and all these lines are 50, 50, 50, which means line 3 is going to be sliced into two parts. 28 MB will go into block 1 and 22 MB will go into block 2, right? So that's when the input split will make sure that same computer has the same line. All right. Now going ahead. So input split, Hadoop divides input into pieces called splits. There is one mapper instance as in there is this class which we created here. Where is our mapper? This is our mapper, right? So Hadoop will be creating its instance. Hadoop will be saying create an object out of this class. That is the mapper's instance. And for that, this will be created one per split. Okay, this will be created one per input split. Input split will be created on top of blocks or block, and your mapper will be instantiated once. Your mapper will be instantiated once for each input split, right? This input split which we are talking about right now, you can think of it as bunch of rows or bunch of lines. Each input split is like bunch of rows or bunch of line. In our text word count example, input split means maybe 1000 rows, 1000 lines or 50 lines or 100 lines. Okay? And for each input split is basically composed of multiple records. In our example of word count, the record means a line. Okay, records mean a record means a single line, meaning a line separated by new line character, right? So on each record, your map function will be called. The way our map function was called on each line. Similarly, in case your input split is composed of different kind of records, say for example, you are talking about input split containing uh, database records, say bunch of rows. In case of HBase, in those cases, the record will be a single row, right? Or you are doing a natural text processing and you devised a mechanism such that your each input split is essentially multiple paragraphs, and each record is equivalent to a single paragraph. All right, now that's how the raw blocks are converted into logical entities and fed to your program. So input splits are customizable. You can create your own kind of input splits. Instead of line by line, you could create something else. You can say each record contains two lines at a time. All right. Now, question remains that how big our input split should be. So it is up to your code. You can customize it as I'm telling you. So it will be up to you. But make sure if you create very small input split as compared to the block size, then you will have too much of an overhead of transferring data from multiple machines to a single machine, right? And if your input split is bigger than a block, again the overhead will go away. So the general strategy is to keep input split as much as closer to the block size, right? So a good split size is equal to the block size, right? So a record is essentially a single entity, the smallest entity on which map operates. Okay, input split is composed of multiple records, and map function is applied on each record, and the record is a logical entity. Analogy is in RDBMS case, a row is a record. Input format creates the records. All right. The example, there are lots of input formats available by default to you. The first one is text input format. The one which we used was by default, the input format is text. Okay. Okay, here we missed one point. Who creates input split? It is the input format. Using the input format, the input splits are created. This input formatter will create the input splits for you. Okay. In case of text input format, the input split is a bunch of lines and a record is a line. In case of n line input format, each record is composed of n lines. All right. You can say you can say that I want these many lines per map. Okay. Per map function should be given these many lines. You can specify using this argument in the job parameters. You can say job.properties here in the stub driver. You can say job dot set property conf dot set. You can conf dot set, you can specify like this. Here you can mention this key here like this. Okay. So these are various kinds of input format, and when you will be doing it, you can also tell, yeah, you can also tell, you can also tell here that hey, we are setting up the input format like this. All right. So similarly, You can do a lot of things here. Okay, so here you will have multiple lines per map, and you will have to change the logic accordingly. You can try it out and see what happens. Now, in case you want your input format to be fixed length, okay? In case your input files, each record is always of fixed length. In those cases, you can use fixed length input format. All right. In the our previous case, we were splitting the records by new line, and each line was a record. And then in n case, we were saying that give more than one record to mapper. In case your input data is fixed file format, then you can utilize this, and you can also set the record length like this. Okay. In lot of data, when you get the data from somewhere, in lot of cases the input data is of each record is a fixed format. All right. Sometimes sometimes your input data is in the form of property files, key equals value kind of format. In those cases, this is a very useful thing. All right, you can utilize these kind of customizations further, whether you want to separate key value by colon or equal to or whatever you want to do. Okay, in case in case you are processing a lot of binary files, if you have got lot of small binary files, say lot of small gifs or lots of, say you are processing the profile picture of thousands of people or millions of people, you are processing the profile pictures using Hadoop on multiple nodes, right? Say you are trying to compute the distance between eyes, average distance between eyes on o- on the basis of the LinkedIn profile of people, right? So what will you do is you'll download all of these files, create something called sequence file input out of these files and feed it to Hadoop. Okay, you'll zip it. You can convert any zips into sequence file input format, and on top of it you'll write MapReduce. Each record will be your each image, and then you can process it and generate whatever you want to do. All right, that is how it is generated. So sequence file input format makes it possible for you to process binary data. All right, are you guys with me or you have slept off? Suppose I want to process audio data, what input format I would suggest? If you want to process any binary file, the best input format is sequence in input format. Okay, so Anand, Eric, Sergio, Johnny, Mark, Rajesh. So are you all up or you have slept away? Great, great. So sometimes it becomes one way, and that's not good. All right, any questions for me till this point? All right, so moving on. Now imagine that right now the way we process the data from HDFS, we were pretty happy. Everything was done by input splitter for us. Okay, there are chances that from inside of your mapper you want to read some other file in HDFS. you can very well do it using using this file system fs command. Okay, let's see if that library is available anywhere to us. Okay, so we can basically say like this. Okay, now this, the config object is in driver. Okay, so we can access the data like this. So we can specify this, all right, as well as from inside mapper it should be fairly possible to use the config object context dot get config. We'll have to use Apache rather than, not this one, this is wrong. Yeah, this is the one. Yeah, got it. We have to use Java one. We were unnecessarily confusing it. So this way you can read an HDFS file inside of your mapper or in the constructor. You can say public step mapper, no, not in constructor. You can't do that in constructor. Okay, maybe we can say this dot get. All right. So no, not in the constructor, you can't access that, but you can access that inside the map. Yeah. So inside the map itself, you can run, you can run, you can basically access the HDFS. Yeah. You can access the HDFS like this. All right. Now under FS, you can say append, or you can say read, or you can say, okay, you can create a file folder, whatever you want to do, you can handle it from here. Okay. So what basically it is fairly possible to write to HDFS, do anything using your mapper code. All right, great. Now there are other nice things to note, such as there is something called splittable gzip. Okay, people realize that since mapper has to be executed on multiple nodes, and parallelly it would be better to create an input format, the file format, which is compressed and still splittable, and this was the ggp splittable. Okay, so it's, and the other format which is compressed and still splittable is aljado. Okay, aljado is the format which basically is very well supported by Hadoop, and we always kept all our log file in aljado format. Okay, so Apache logs, they as they keep on building, so plain text can be compressed. So one way to compress the text is we just use the normal zip and be happy, but uh, but that would not be an ideal solution if you are churning the data of your Apache logs on the cluster. Ideal situation will be to use Algedo. Okay, so Algedo will be decompressed on each node. Part of it, because it is sliceable, it can be splitted. So Algedo will be decompressed, parts of the file will first split it and then uncompressed on each mapper node and then fed to your logic. Your logic need not worry about compressed data. Your logic can think of it as uncompressed data and keep on processing it. Okay, so that is Algedo format. All right. If you have to extend the input split, you can extend it. First, you create something called a class. You basically extend a class called input format. So you can extend the input format. I'll show you that. So here you will see what happened to our CC driver. All right, so here if you see custom reader is there. So first of all, you start by extending an input format. Instead of directly extending input format, I'm extending something called input text format. Input text format, internally if you see it, it basically extends file input format, and which indirectly extends the input format. So basically I created my new kind of format called my nline input format, and that extends this one. And internally all it does, it gives an instance of a record reader, and this record reader is our record reader. This record reader is our own record reader, and it implements a complex process of splitting the file. Here in the initialize, it basically tries to read blocks and create the input split. Okay, so you can create your own input split. Here we have just tried to create a single input split. We have tried to create n lines record reader. Okay, although it is there is not much of a use, but still for the sake of understanding, we have tried to implement n lines record reader. Okay, basically your mapper, instead of getting a single line, it will get multiple lines at the same time. Make sense to you? All right, so you have a look at this code. This code is also available to you. All right, now next is an input split definition can be given here itself. So data flow is clear to everybody. Should I explain this diagram? Is this diagram clear to you? Okay, here there is a network transfer going on. Dash dash line show you the local transfer, while the strong lines show you the network transfer, and the dashed boundary is the node where the work is happening. This dashed boundary, you can see the dashed boundary, and the strong boundary is for each individual MapReduce. Okay, this is the data flow with multiple reducers. So on each machine, what's going on is after the map happened, it's being partitioned immediately. While sorting itself, it is being partitioned before even sorting. Okay, before sorting, the split happens, and individually sorted data gets transferred to separate reducers. Okay, so okay, again the same philosophy which we already talked about, the maximum number of reducers remain the same one. Okay, Now, what we want to discuss right now is the partitioner. Okay, here we talked about something interesting. Just after your mapper gave out key and the values, right? The key and values were created, put in separate buckets. And on what basis should it create these buckets? On what basis should it create two buckets? Right now, do you think if we concatenate part 0 and part 1, will we have the data sorted? Anyone? If we just concatenate part 0 and part 1, will our data be sorted? Okay. So can you do something about it? If you could say that second reducer should get all the keys which are starting with J, K, L, and so on. And all the keys which are starting with A to J should go to first reducer. If we do that, then we should be able to join part 0 and part 1 and have the sorted data, right? So that is the role of the partitioner. Partitioner is the one which can help you control how to separate out the data, how to split it, and how many partitions need to be created every time. Anybody? How many partitions have to be created? So here the partitions role will be take key values and generate n number of partitions based on reducers. That is correct. Great. Now let me show you my partitioner. So this is my partitioner, or my partitioner could be very simple as like this. Okay, you'll see this. This is my partitioner. It says that if my key length is greater than 0, okay, or we can say greater than equal to 0, or we can say like this: if key length is 0, send it to the first reducer. If key length is 0, okay, else if, although we don't require else because before that itself the control will return, if our, okay, if the key length is greater than 0, then and key is less than k, send it to the first reducer, otherwise send it to the second reducer. So blank lines and words starting with a or numerics, they will all go to the first reducer, right? And rest will go to the second reducer. Sounds good to you? Actually, our partitioner was different. Our partitioner is this folder. Okay. In case you had, say, three reducers, okay, in case you had three reducers, your logic will be different here. Your logic will be saying, for your logic will be like this. I'll show you. For A to F, return 0. For less than P, send it to 1, else send it to 2. Okay. So this way we'll have three reducers. Let's set the three reducers here. Let's just say reducers are 3, and this is our partitioner. To specify partitioner, we say job.set partitioner, and this is our partitioner class. This is our partitioner class. Okay. Now let's start with this. Again, let's compile it. It's automatically compiled. Here we have set project build automatically, so it's building automatically. And when we export, it's already built. Sounds good. Now let's copy it. What is wrong? Oh, my caps lock is on. Okay. Now let's run our, so I say partition, that's our output folder. And this time we should have 3 parts. URL to track is here. That is something I always like to do. So to starting the work, so it says 3 reduces, okay, and it's starting the work. Oh, it says incomplete HDFS URL. We forgot to delete our HDFS things. Yeah, this we have to delete this. Also, I wanted to show you a few more things. One is here inside the mapper, we are doing further more cleaning up. Actually, we were showing you a different mapper. So we were basically removing all the non-numeric characters and also converting the word into lowercase. And here I'm printing something called to error output. This is what I'm printing. Okay, this is what I'm printing. And here you can see that we should be able to get this in somewhere. We have to find it out. Where does this go? Okay, and in stub reducer there is again we have put some log. This is great for debugging. Lot of times you will say my map reducer are not generating a proper output. In those cases, put the error logs and I'll show you how to find that out. Okay, so let's export it again. We are exporting it again. All right, and let's copy it. So I'm copying it again. Partition 1 is our output folder. Okay, let's go back to the URL. All right, let's go back here and see what's going on. Not timeline service, we want the job tracker. We want this URL. All right, is everyone with me? So now you see the mapper goes little slow because it is creating three parts, and then we'll be sending to reducers. Okay, and parallelly, let's open the hue also. There we will observe our folder in which we are expecting our output somewhere. Let's go to that folder. All right, so it has finished. This will also refresh after some time, and let's see what happened. Okay, so it has taken more time, you see, because the reduce as we are increasing reducers, it is increasing because our data and actual work is smaller. That is why. By increasing reducers, we have unnecessarily increased the network traffic. You see, initially it was something like 40 seconds. After that, it became this. Now let's go to file system. What did it generate? This is a folder where we want to go. So here you see three parts. One is this. So here it's all zeros up to what? Let's go to last block. Up to E. We see up to E. And if you go to second part, you'll see starting with F and till O, right? So is this clear to everybody? So we partitioned the data at our own whims and fancies. We were able to control it. The other thing I wanted to demonstrate you is the log file. So it is sorted. It is no, it's not sorted by frequencies. That's not what I was trying to do. I was saying that in case you combine part 0, part 1, part 2 just back to back, the whole data will be sorted. Earlier, in our earlier word count, first word goes to the first reducer, second word goes to the second reducer, then third word goes to the first reducer, and so on. The hash code was fairly random. Okay, the hash code was fairly distributed, fairly, you can say, randomized earlier. Now it is based on our own strategy. We said all the things up to E send it to first reducer, all the keys up to K, up to O send it to second reducer, and rest send it to third reducer. All right. Now other thing I wanted to Now I wanted to show you the logs. This is a common question which everybody asks, that where did whatever I wrote to the standard output, where did it go? Okay, let's go inside the job. Let's say we go into map. Under the map we have got a task, and under the task you will see logs, and here this is a mapper is what is being written all around. You can see that this is our log what we created. We had written like this, see. All right, similarly you will see that under reduce, so under a task you have got map and reduce, and under map and reduce you have got again the map reduce tasks, and there will be multiple attempts for each one. The first attempt is this which has succeeded, and you see this is how you debug your map reduce. Sounds good to you? Great. All right, so should we break here and discuss rest of the things tomorrow? All right, tomorrow we'll talk about something called combiner and then data locality. Yep, you guys should try it out and let me know. At least try to run this program, whatever we have given. Yeah, next weekend. That's correct. Whatever we did today, Just try to run it as is, and I assure you, by the time you finish running your own program, you will be fairly confident in creating the new one. So, more important than the Java code is actually being able to run it and understand it, what's going on, and then you will be automatically confident in writing your map reduces. Okay, so see you on the next weekend. What is the version of Hadoop are we using now? So I think we are using Hadoop minus version. So it says that 2.5, not 2.5. We are using 2.4, Hadoop 2.4. Okay. Okay. So it will take maybe by tomorrow morning it will be uploaded. Meaning it will take around 6 to 7 hours from now. All right. See you next week. Have a great weekend. Have a great week actually. Okay. I look forward to your answers, and do write us at hadoop at nobigdata.com. All right. At that, if you write to that one, you might get a quick answer, quick response. If you write to me personally, there are high chances that I may not be able to answer very quickly. And also, I try to be very brief in the email. See you. Have a great week ahead.